Welcome to the multi-story building analysis after a sudden column loss webinar. My name is Alex, a structural engineer at S-Frame Software, and I'll be leading this presentation today. I'm also joined by a few of my colleagues that will try to answer your questions as you submit them. If we run out of time, they will respond and follow up after the webinar. And here's the model we're going to look at. It's a 5-story steel and concrete building. And we will study the dynamic behavior after a sudden column loss, as you can see here in the left hand side. We prepared this case study just to guide you through the procedure to run the dynamic analysis and verify the properties of the structure after the sudden column loss. We start this presentation by looking at how we are going to formulate our model. Then we will look at the static analysis to see the influence of the column that has been removed. And finally, we will perform a dynamic analysis and observe the dynamic response of the building once the column is removed. At the end, we wrap things up with a summary of this presentation before opening the floor to any questions you may have. Starting with the model formulation, you may be wondering why running a vibration analysis. The idea is to understand the dynamic behavior of the structure, which is very important. For instance, if we have a stiff structure with a high natural frequency, it will behave completely different when compared to a soft structure. And determining the natural frequencies is a very important part of any structural analysis. It also gives us the opportunity to determine the damping coefficients, which is what we are looking for this case. We run the analysis and conclude any assumptions we made are correct, and we will see more of this in a second. Another nice feature or ability of the vibration analysis is that it doesn't depend on any loading. We can actually run it earlier in the modeling process before applying our loads, and this will help us identify any modeling errors before we put a lot of work and time into our project or structure. Let's jump to the demo part of the presentation. Here's the structure we just were looking at. Again, this is a 5-story steel and concrete building. And first of all, we would like to have a better understanding on the dynamic properties of this structure by performing a vibration analysis. So if we go to Analyze and run an unstressed vibration analysis to see the dynamic behavior of this structure. And once ready, you can just hit a key on your keyboard, and it will take you to the graphical results window to show the mode shapes and the frequencies periods for this structure. So if I go to the mode shape tool, you can see the different periods here, and you can see the different mode shapes here. Another option will be go to the numerical results window to see the actual frequencies. We see that varies from 0.6 for mode shape 1, 0.8 mode shape 2, 2.18, 2.4 for mode shape number 4. But you can always use S-View if you go to run S-View, and it just take a couple of seconds to open. This is our validation and collaboration tool to verify also the results after running an analysis. And once it's loaded, you can see, if you rotate, you can see the missing column is here for the vibration results for mode shape number 1. This is a lateral mode shape in the X and Y, maybe with some torsion. Then we move to the second mode shape. We can see we have a vertical movement here. Maybe it's a bit exaggerated, but I can always decrease it, maybe 0.2. If we check mode shape 3, we can see it's isolated to this column. Mode shape 4, very similar. And let's just take a look at a couple of them. Mode shape 5 seems to be global mode shape. what we do get from that is that we get the different frequencies and different mode shapes. And from this, we can say that mode shapes 2, 3, and 4, which we have investigated, seems to be the primarily mode shapes around the removed column, because of the floor is moving up and down in these modes around the column location. These 3 mode shapes have a frequency range of 0.85 to 2.4 Hz, and we're assuming that the column loss is primarily due to the vertical motion, so we're ignoring any lateral loading that could come from the column removal. With this information, we can then calculate the damping parameters. We're going to assume the following damping ratios of 0.01 at an angular frequency of 5.31 radians per second and 0.03 at a frequency of 15.04 radians per second. And we're assuming these damping ratios are reasonable and typical values for this type of structure. From this, we can calculate the Rayleigh damping coefficients, alpha and beta, using these formulas, based on our vibration analysis results and assumed damping ratios. We found that alpha gave us a value that equals 0.323146 and beta equals 0.004012. And we actually have a spreadsheet template to calculate alpha and beta if you know the different damping parameters and frequencies. So if you're interested in that spreadsheet, please send us an email and we will be happy to share that document with you. You may be wondering why we went through all the trouble of calculating those alpha and beta Rayleigh damping parameters. And it is mostly because these values can be used for damping or structure transient response due to the column loss when running a time history analysis. You can see here in the time history analysis dialog, you have an area where you can input those Rayleigh damping coefficients. Now we also need to understand the original influence of that removed column, and again, that column wasn't completely unloaded when it was there, so we need to understand exactly how much axial load exists in that column prior to the removal. To do this, we are going to run a linear static analysis. It is important to note that since we removed the column, we need to determine how much upward force on the floor that column needs to absorb. And we're going to do this by applying a pin support at the point where the column will have met the floor. And what we are interested in when running the static analysis is the vertical reaction at that support. Here is the model we're going to use. This model is slightly different from the previous model. It just have one change. So if we rotate the model and just looking at the support tool, and if we zoom in with the zoom window, just highlight that area, we can see we have a pin support at the top at this node, which represents the top of the column that is missing. And this is constrained in the X, Y, and Z translation directions. What I'm interested in is in the vertical Z reaction at this point, so I can note the force that this column is contributing to the rest of the building. What I'm going to do is, with a self-weight load case that I already defined, I'm just going to go to Analyze and run a linear static analysis to check on my results. Now that I'm in the graphical results window, I can switch to the reaction tool, select my gravitational load case, the self-weight, and just focus on the vertical Z reaction. If we zoom in at this point, we can see we have a value of 656 kilonewtons. This is the force of my column. So please bear that number in mind. And if we go back to our presentation, so mentioning this once again, under gravitational loading, the column will provide around 656 kilonewtons of upwards vertical reaction force, and this will be our initial force for the time history load that we're going to apply in just a second. And we're going to represent the column before it's removed with an upward force with this magnitude, as you can see here. Now we're at the point where our model is formulated, and we need to see how it responds due to the loss of the column through a linear dynamic time history analysis. We start by applying a time-varying upwards load at the column location to represent the support from the column. There will be a transient response from this initial upward force, and we will allow it to die out and quickly release the load to represent the loss of the column. Just by looking at this graph here, we start off by applying this 656 kilonewton load, and we apply it for a period of 4 seconds. We should give enough time to the transient response of the structure that just got loaded suddenly for that response to die out. And once that response has died out, we will release that load very quickly in a period of 0.2 seconds to represent the sudden loss of that column. And all the actual load that will have been applied at the column will then be removed, going back to 0. When we run a time history analysis, we're going to consider both the time-dependent loading, as we can see in the bottom of the screen, and the self-weight load case, which is representing the gravitational load. When we run the time history analysis, it's important that we use the correct time step integration. For this case, we have a sudden removal of a column, and we need to be able to capture this behavior in our analysis. The variable time step integration is the most efficient way to do this. We're going to use a very small initial time step size of 0.01 seconds. We have a minimum time step size of 0.000001 seconds, a maximum time step of 0.01 seconds, and a critical jerk of 0.01. For those of you who haven't used it before, in a variable time step integration is the maximum way of change in acceleration in the variable time step integration algorithm, which will allow without reducing the time step size. Essentially, what this is doing is varying the size of the time step in this window here between the maximum and minimum size to be able to represent the peaks as accurate as possible. In the case the algorithm senses a critical jerk greater than this magnitude of 0.01, it will then introduce another time step, and it will allow to integrate the result much better than we could do with the defaults in the constant time step integration. And the reason we want to do this is because we want to accurately capture the dynamic behavior of our structure. And if we have two larger time steps, we're not going to be able to capture that, especially with a very sudden loading. With a very sudden loading, it could be possible that the loading could occur between two different time steps, and it could be missed entirely. So I open a new S-frame model, very similar to the one we've been working with. I just want to show you the load that I have applied to this model. So if I go switch to the loads window, I can select my column force and then take a look at the time history tool. If I right click, I can see I have a nodal excitation applied of 656 kilonewtons for the first 4 seconds, and then drops back suddenly, simulating that column removal, which lasts 0.2 seconds and then stays at 0. So just to show you, if I zoom in, I can show you the load where it's applied. It's in this node, which simulates the force that the column that is missing is contributing, and then up to 4 seconds, and then with the column removal, is not applied anymore. Once we're ready to run our analysis, we'll go to the Analyze command, select Linear Dynamic Time History Analysis, select our variable time step integration with the parameters we mentioned before, and also we can introduce our Rayleigh damping coefficients to help to the transient response die out, or alpha and beta, and click OK to run our analysis. So I just went ahead and run an analysis. You can also access this information in the numerical results window. You can see all the information for the joint of interest, and you can copy paste these tables into Excel to generate a graph and see the dynamic response. Just before going over into that, I'm going to show you the graph I created. I just want to show you the SView model I have here. So after running an analysis, I just open SView, selected my load combination, and we can see if I just play the display button starting from 0, I can see a certain load that is applied to my column for 4 seconds until dies out the transient response, and then when the column is removed, it goes down and it doesn't go into its initial position anymore. So I'll just stop the animation, go back into the presentation, and then go into our slides. So as I mentioned, I took the time to export the result data into Excel and generate this graph. This is the deflection response we get at the joint, which is at the top of the column that was suddenly removed when we applied our dynamic load. You can see here exactly how it's behaving, starting at 0 seconds, and again we apply 656 kilonewtons of load, which caused a little bit of excitation and dies out due to the damping in our structure, and you can see it's dying at around 4 seconds. But at 4 seconds, at the same time, we have the removal of this column, and this results in a large change in our displacement. So basically the joint moved around 85 millimeters, and it shoots back up and oscillates around a certain point where it looks to be converging into an equilibrium. And again, we can see that those damping parameters we introduced are taking effect. We can really see the effect of the removed column, and looking at the built-in response again, we see the oscillation at around 55 millimeters of deflection is in the negative z direction. Now we also see that in the span around 2.5 seconds, we have 6 cycles of oscillation. From this, we can calculate the frequency of this oscillation, which equals to 2.4 Hertz. So we took the 2.5 seconds divided by 6 cycles and to calculate the frequency value at 1 period of oscillation. Now let's compare that to our vibration analysis results that we saw before. We can see that value matches our fourth mode of frequency almost exactly. So the vibration analysis really gave us a good estimate to understand what sort of oscillation we get once we started to remove the column. As you can imagine, there are some major changes in forces and stresses once the column is removed. Just to give you a quick summary, in this table, we took a measure of each mode of where each of the maximum forces occur before and after the column removal. So before the column removal, we can see moments, maximum moments and shear forces, and also the values after the removal. And we can see the increase, which is a substantial change. One thing I would like to point out is that we have a list where each one of these shells are numbered, and you don't have the model, so it may be difficult to verify, but these are adjacent to the nearest remaining columns. And again, those columns are supporting the additional load that was originally supported before the column removal. So these shells are now being stressed even further. We also ran a steel code check before and after the removal of the column, and the governing load check was the same in both cases. The axial compression and bending overall the member strength check. You can evidence the utilization ratio was dramatically different, and what would have been a passing code check before the removal with the adjacent column now is having an overloading column instead after this removal. This really give us an understanding of the magnitude of effects that occur before and after the column removal. If we look back into our deflection response once again, we can see there's a large influence from dynamics. The deflection, if we look where it's converging, and around 55 millimeters, it gives us an understanding of the final equilibrium point due to the inertia of the floor. That is going down and then back up and all due to dynamics. The dynamic effects clearly have a great impact on the magnitude of forces, moments, stresses, and deflections. If we were to very slowly load this floor, the dynamic effects will not be as noticeable, and without any oscillation overshooting the structure, this will settle into the equilibrium position as we run a static analysis. So the delta I show in the last slide is caused by this inertia on the floor in the vertical z direction. So in this presentation, we started off by getting a better understanding of our structure and running a vibration analysis to understand the dynamic properties. We chose to use a time history load to represent the influence of our original column before the removal, and ran an initial static analysis to see the influence of the column in terms of actual load prior its removal. And once we have all that information, we can run then the time history analysis to see the influence of that removal of the column and see how the structure behaves once that is done. I just want to bring a couple of summarizing points before opening the floor to any questions in the next slide. So in summary, by breaking down this complex problem into 3 different steps, as you already saw, we can get a better understanding from the dynamic response of the structure, which experiences a sudden loss of the column. We made a couple of assumptions, remember, and with that we can only consider this as an estimate, meaning that the forces, stress, deflections, all the outcome that we found, in a real world case, the effects could be higher. There's a couple of you who asked for a copy of this presentation to have as a reference. I just want to let you guys know that this example is all based from a document we have available in the help system. So I would suggest you taking a look at this model, at this document, which has all the steps we follow during today's presentation and in much better detail. So here you can see all the information that is related to this structure and its dynamic response after the column removal. Here's another question. Why are we using the variable time step integration and not the constant time step for this exercise? Well, as you may know, when you run a linear dynamic time history analysis, we see both options, constant and variable. So with a constant variable time step integration, essentially what this is doing is allowing us to introduce a number of time steps that will have a consistent time steps through all the analysis. And the variable time step integration, you use an initial time step size, and you define the range of time steps, and you can use, by using the critical jerk, the software will be able to detect where we might want to focus our attention in the analysis. So it basically is looking for any points of interest in the curve or any spikes, and will focus higher frequencies of time steps in those locations. In that way, it won't have to spend too much time in the less interested parts of the curve. Remember that given the same number of time steps, the variable time step integration method is always more accurate, and the variable time step default parameters are good for most situations. But we always encourage to the engineers to double check these parameters so they can adjust according to their requirements. Thank you for the question. I have time for one more question, and this one is related to the damping coefficients we calculated. So again, for those values, we actually use a spreadsheet that is available to you upon request. So you can enter your damping coefficients, natural frequencies, and from there you can calculate the alpha and beta values automatically. You can also use the formulas that are referenced in the document and in this presentation to calculate those values.